In 1974, General Electric and a French state-owned company called Snecma signed an agreement to build a commercial jet engine together. The American government had initially blocked the deal because GE's engine core was derived from technology powering the U.S. Air Force's B-1 bomber. It took a personal intervention from President Nixon to get the export license approved. The engine they built, the CFM 56, went on to power the Boeing 737 and the Airbus A320. Over 32,000 were delivered. It became the best-selling commercial turbofan in history.
But Boeing had nothing to do with building it. Neither did Airbus. Every commercial plane either company has ever built runs on an engine they didn't make. The 737 MAX, the A320neo, the 787, the A350, all of them powered by companies most passengers have never heard of. And that arrangement is older than the jet engine itself.
To understand why the two most powerful companies in aviation don't make their most important part, you have to understand what it actually takes to build one. Inside a jet engine, the turbine blade spinning gases hotter than 1650 degrees Celsius. That's above the melting point of most metals. The blades are made from a nickel superalloy grown as a single continuous crystal. No grain boundaries because grain boundaries are where metal fails under sustained extreme heat. Only 5 countries have independently mastered the complete manufacturing chain: the United States, the United Kingdom, France, Russia, and China. Germany cannot do it. Japan cannot do it. Canada, Brazil, South Korea, none of them. That is the barrier Boeing and Airbus would be clearing on day one. Consider what that part costs against everything else on the plane. A Boeing 737 MAX 8 lists at around $130 million. The two CFM LEAP 1B engines that power it list at $15 million each, $30 million of the total before a single panel of fuselage is riveted together. Across a commercial aircraft, engines account for roughly 20% of total manufacturing cost. The entire fuselage accounts for a similar share. Wings around 15%. Landing gear roughly 3%. The engine costs as much to build as the part of the plane most people would assume is the hardest thing to make. And then there's the cost to develop one. Pratt & Whitney spent $10 billion on their geared turbine fan, the GTF, which delivered 20% better fuel efficiency and entered service in 2016. Then, a powder metal contamination defect emerged in critical components. Pratt took a $3 billion write-down. By 2025, they had paid over $1 billion in cash compensation to airlines. Spirit Airlines alone negotiated between $150 and $200 million in credits. Airbus launched a formal damages claim. In the first 2 months of 2026, Airbus delivered 20% fewer aircraft in the same period in 2025. Not because of anything wrong with the airframes, but because Pratt couldn't supply engines. Rolls Royce spent $11 billion on R&D between 2010 and 2018 just to remain competitive, and separately set aside £1.38 billion to fix one problem on one engine variant, the Trent 1000. That is the cost of staying in the game, not entering it.
Boeing and Airbus have watched this play out since the beginning. In 1971, Rolls Royce won the contract to power Lockheed's L-1011 TriStar with the RB211. The original carbon fiber fan blades failed bird strike testing and had to be redesigned in titanium. By September 1970, development costs had reached £170 million against an original estimate of £75 million. Production costs per engine exceeded the £230,000 selling price. On February 4, 1971, Rolls-Royce declared bankruptcy. The British government nationalized the Aero Engine division and absorbed losses exceeding £200 million. The 2-year delay handed the market to the DC-10. The L-1011 never recovered. One engine program, 2 companies nearly destroyed. The separation between airframe and engine goes back further. In 1929, Boeing and Pratt & Whitney were the same company, United Aircraft and Transport, controlling planes, engines, and the airline flying them. The Air Mail Act of 1934 banned the same company from manufacturing both aircraft and engines. A congressional response to a procurement scandal 90 years ago is still the reason your plane's engine has a different logo than the fuselage. Boeing did try to get back in. Through the 1950s and 1960s, the company ran a gas turbine division that produced more than 2,000 engines. It never made money. By April 1968, Boeing closed it permanently and redirected every engineer and every dollar toward the 747. The decision that made Boeing dominant was the decision to stop competing with GE and Pratt & Whitney. The structure that followed served the both companies in ways no one planned. The A320neo flies with either a CFM LEAP or a Pratt & Whitney GTF. The 787 flies with either a GE GenX or a Rolls Royce Trent 1000. If Boeing built its own engine, it would become a competitor to the suppliers powering every program it runs. Airlines would question whether a Boeing engine was designed to optimize Boeing's margins or their own operating costs. The revenue captured from engine sales would be offset by airframe orders lost. The optionality isn't a gap in the business model, it's load-bearing. Engine makers also operate on a model with no equivalent in airframe. Rolls Royce introduced it in 1962, power by the hour. Airlines pay a fixed rate per flying hour. The manufacturer covers maintenance and parts across the engine's service life. Hardware is sold at thin margins. Revenue comes over the following 25 to 40 years. GE Aerospace derived 70% of its total revenue from aftermarket services in 2025, at margins above 26%. Boeing and Airbus deliver aircraft and collect payment. Engine makers deliver aircraft and start a revenue relationship that outlasts the airframe.
China understood this problem and spent 2 decades trying to solve it. The state-backed Aero Engine Corporation of China began developing the CJ1000A, a domestic turbofan to replace CFM LEAP engines on the Comac C919 in the early 2000s. Originally targeted for certification in 2020, the program has slipped repeatedly. Mass production is not expected before 2030. Until then, every C919 flies on CFM LEAP engines. In 2025, when trade tensions escalated, the United States suspended export licenses for those engines. The aircraft existed. The orders existed. None of it mattered. China had been working on this problem for 20 years and still hadn't solved it, which tells you more about what the engine business actually requires than any cost figure can. Boeing and Airbus don't face that problem because they never tried to solve it. They build the planes. Someone else builds the engine. And a CFM56, the engine Nixon had to personally approve, has now logged more than 1 billion flight hours. The most important part of the plane has always belonged to someone else. It was that way by design, and it turned out to be the right design.